So I'm trying to close all the topics, and for some reason, I realized that I basically lost the VQLS like Jupyter notebook I was playing with. Yay! Welcome to real life learning. So if you check out quantum intuition channel, so there. Should be gonna mute myself. So here, if you take a look at the videos, I should organize this better, I guess. But there, do I have it in a playlist? I think I should have it in playlists. VQLS. Oh yeah, here you go. So there's a list of. Oh, it's already 6 videos. Wow. Okay, I didn't know I did so much work on this. Okay, but basically, I didn't know at the end of the last video how, why because my idea was I wanted to have I wanted to play with a different cost function. Okay, so I wanted to play with a different cost function where instead of using these here, and I don't know if my pen works because I dropped it the other day. So instead of using, oh yeah, I think it's not going to work well. And instead of using these here, right, where it's kind of being developed. Sorry, that's just a Hamilton. That's not a cost function. That's the cost function, the expectation value of these, right? And then these is basically defined as do this. We subtract it from another number. It's the projection. So it's kind of the projection on B, is it? Like B being the solution of the equation system, if I remember well. And there's some normalization involved and whatnot. And then I was like, why can't we just use the overlap directly, right? So my idea was we'll just implement the overlap, right? Like the overlap function. Remember, this is the it's basically a function that tells you how sort of how equal two states are, right? And so I thought, why don't you just use these? But I got stuck, if I remember well, in the last video where I realized. Let me see. I'll just mute myself, but I think it's somewhere here. So I got it to work in a way that it was. It got it to work pretty well, actually, if I remember well. But it was not optimal, and I suspect the reason is because it's not the right way to build a cost function. So my suspicion is that if we have, trying to think how to explain this. So if what we have is we have blue. So if we have our matrix A, we have our vector X, right? And then this is supposed to be B. It's broken. I think it's not working really well. So like the thing is, if that would be it, then it's kind of okay, right? Like you could do it. The problem is A has to be decomposed because A, it's not something we can express generally always as a single matrix, right? So it's decomposed into the sum of Pauli matrices at least in this particular example. So A is really sort of A1 plus A2. And so this means that you got to kind of do the problem. Oh my God, that's just awful. I think I broke the thing. I got to buy a new one. And so, I basically resorted to kind of doing the overlap function for just one of those. So like A1, A sub 1, then X, right? And then the overlap with B. But I think that's the problem. That's wrong, right? Because how do I combine the two overlap results into one cost function? Like on one side I'm optimizing for, it's like it's wrong, right? Because the sum of the sum of these overlaps, it's not guaranteeing me that I get an actual overlap, the one that I want. And so I wanted to, for today's video, to try to test or shows it with a smaller example that this doesn't work. I asked in Twitter, I asked like I think a couple days ago, the question uh, of like, yeah. So Marco replied, like, it does a really cool reply. Like, I really recommend you guys read this thread. So I asked basically, and it was just to learn more about designer classical as well as quantum cost functions, because that's definitely a topic that I'm interested in. But like, I think so. He says operationally meaningful, right? Small values mean something, large values mean something. Computable, efficiently estimated, trainable. So the bar and plateau is, this is what it's something that I've seen before, but I really don't know what is these. So I should probably Google that. And certifiable infrastructure that need knowledge you might not have. Don't use cost at distance approach. So this is really insightful. Now, it just, if you think about these, having the overlaps, calculating the overlap of each portion doesn't make any sense, because I can't really make a cost function, right? Like, if let's make it as simple as, like, let's simplify the problem and say that, I don't know, I have like, let's imagine that my A1 is just a Y. It's like just a rotation. What would be a good example for these? What would be a good example for these? I mean, even just something with the identity, would it be? So try to find an example where I could just, with a small, just maybe one qubit, show that it doesn't work. And I'm thinking along the lines of having some sort of just a rotation along just an RY, like an X rotation, and and I know, like a Z rotation, an X rotation and a Y rotation, right? Or an X rotation and a Z rotation. And kind of try to say, approximate, like try to train something, like try to train, try to do optimization on, on something like that, like just with the parameters there, and let me see, and the parameters of the rotations, and see if we can, for example, I don't know, go to the state, like, I don't know, what you get when if you go like on the plus state and then you add a t, right, or something like these. Because I'm saying, I'm sensing this should be enough or easy to understand that it doesn't work. Let me show you here, maybe better. So the target state for me would be something like these, right? And I wanna kind of do these with the sum of two circuits. One is like an RY rotation, and another one is an RZ rotation. It's so what's the meaning of these actually? If I just say like an RY rotation, right, will never take me there. So the best I'll do, is probably pi divided by 2. And if I do a Hadamard test on these, not the Hadamard test, but the destructive thing. How is that? How is this? How is this done? Damn, why did I trash the? I was cleaning up and shouldn't have done that. Here you go, just like that, exactly. So this tells you how close the states are if I do these, and it was these plus these minus these, I think, right? So that's really the closer I'll get, because if I go, say, let me put blocks spheres in here. If I go pi divided by 4, right, that gets bigger. Like, that's not going to get smaller than 7. Like, if I actually do just d, it's not going to get smaller than 7. What is it doing? It's going to be easier if I do it like this, I think. That's not going to be smaller than 7. I think that's the smallest you can get. Yeah, exactly. That's the smallest you can get. That's exactly by then. Exactly then. So what would be the meaning of, like, why? It's like it just doesn't make sense. The addition of these two things doesn't make sense. Like, I can't just take that and add it to something else. Like, you know what I mean? It's like I can't combine. Like, I could train something that like would be a product. So I would just do these and then do these. And if I do that, there's a point where this gets to 0 or almost. Oh, okay, yeah, because that's this kind of weird stuff in here. Yeah, because I'm doing like the animated thing, right? But if I would do if I would, it's just as simple as like if I would do these and then I would do these, then there you are, right? It's 0, and so I'd visit that state for sure if I would train those two things. If I would use like gradient descent or something on those two things, but what I was trying to do is I was trying to add things, and that doesn't make any sense. I was trying to add the results of the two things overlapping with B, and that just, it's like mixing apples and oranges. I think that's not a good cost function at all, because it doesn't even have a ceiling, or should it have a ceiling? I don't know, but it's not. It's a function that it's not. It's like saying, I could do something like these, right? But that's the best I'll get. And if I just now say no, and now the next thing I want to do is I want to do just with just with the z's, right? Like it's like the best I'm getting, right? It's these, right? So it doesn't move at all. So this is 75 as 50, right? It's 50%. 50 should be 0 actually. How did you calculate that? I thought it was, no, I think it's plus minus or something like this, is it? The Hadamard, the overlap test. Overlap. I forgot what the papers are. I should keep track of all these. That's really bad. That's really bad. I think it was one of those papers because this one is clicked, so I think it had to be this one. Clicked, visited. I think it had to be this one. Yeah. Exactly. Yeah, one says it's -1. But then it's not. That's one. There shouldn't be any. Oh, that's the problem. That's the overlap test, right? It's doing. Okay, so functionality there works. Okay, that's the problem. Do I just keep that? Whatever. This is definitely not. Well, yeah, because there should be so. Okay, the opposite would be if they would be completely opposite, like so in opposite directions in the blocks here. I think if I would do these and then I would do -s and -t. Exactly. Now you've got like 25 plus 25 minus 50, and that's 0. That's kind of when you're the opposite. But in this case, the best I'd get would be 50%. So, like, what do I do, right? Like, I can't. It's not, the fact that they would both overlap. It doesn't mean it's the correct solution for a VQLS, right? Like, it doesn't mean it's the correct solution because actually it won't be. Maybe it would, because if I would add them, then it would just be twice the vector. So I would kind of have to maybe split that. But still, thinking whether that would work or not, because if I so first I'm checking the overlap with the vector. I will be checking the overlap with B, which is the solution of these, right? This is what we're checking. The overlap with A1. And at the same time, then the overlap with A2. And and I would expect that if I combine them as like each contributing 50%, if I would get a 1, that would be the best solution, because it means that both components are then along the same direction. But it would be wrong because if I would find a solution where the A1 component, for example, half overlaps, or this, or overlaps like a lot. It kind of overlap more than one, so it kind of overlap more than 50% if that's a contribution. I don't want to code the whole thing again. It was a long. I'd have to go and copy. Because the point of the cost function in here, right, is that you're taking in consideration the whole thing, and then you're decomposing these. And at the end you get, because you're using expectation values, you can take those components out of the equation. Not out, but like you can take the sums out, exactly. Because you're using expectation values. And because you're using expectation values, you can take these sums out. And so that's a correct cost function, right? Because it's the sum of all the expectation values. Yeah. But, okay, so this is the way that I should, but in my toy example, the sum of the overlaps is not the total overlap. Even if I would make up that they contribute 50% or whatever. Because in the example here that I'm trying to make, if this would be a, let's say the identity maybe, right? And or it's just like the Hadamard. That would be one equation. So how would I do this? If I would say, for example, two equations, right? Like that would be the simplest thing to do. So I would say, I don't know. I already did two equations, so could I just do it with one equation and solve it here? No, I don't know. I'm not the happiest with this. I'm like slacking around because I don't want to peel that again. I'm trying to find a way to understand or to prove whether this is something that trying to find an example where I could simply verify that that's just the wrong approach, and yeah, that's the that'll be it, right? So so if I would have a system of equations that is the simplest possible, right? That does, I mean, I think I even had like x plus y equals, I think it was 2 what I was doing, and then x minus y equals 0, right? I think that was what I was doing. So then I get like the matrix is 1, 1, 1, minus 1. Sorry, but my pen is broke. This is 2, 0. Yeah, that's 1 qubit, right? Yeah, that's 1 qubit. And so what was that then? So yeah, 1 qubit example. Okay, we are I was doing okay here because we just need 1 qubit, right? Because A is like that. Yeah, the Hadamard, exactly. Look at this. So in theory, X, right? Supposed to. I feel I became. So now I want to do the Hadamard test. It's a perfect solution. So the Hadamard test I was doing, and then I was trying to solve the whole thing, and it's like X plus Z. 1, 1. In theory, I should probably rewatch all these. Equal to these. And if I multiply that, it's basically these and 0. Right? Because here I made a mess, I remember, with the probabilities. And this is right, because that's so rusty, man. Yeah, that was a funny video, I remember. See if that works with the optimizer and it finds the right thing. And so, the idea is you want to minimize that, right? So, okay, the next video is I'm going to try to actually do that in Circ or something is wrong with my cost function. Given what's wrong? So I don't know. I feel I'm just losing time, and I don't want to lose time. I don't like losing time. How can I check that? How can I check that? How can I check that that this really doesn't work, right? If this is the if then I complain that I spoil the bands. If this is my yeah, the thing, right? So the system of equations, and I want to decompose these. Why would I need to decompose these? Why would I need to decompose these into two things, though? This is what I don't get. What I was doing with these two circuits. What was the identity? Because I was doing the identity plus the ZK. Was I? Mm. 031425 and then 0 overlap test. That's what I should do first. That's the overlap test, right? It's doing 031425 and then 012. Yeah. Should apply the overlap test. Sorry. Yeah. Should apply the overlap test. Sorry. And I was applying the overlap. Why was applying it twice if this is just a Hadamard without the 1 divided for the square root of 2? Then I should just I shouldn't really do anything twice. I should just optimize for that, right? So I should just find a gate that multiplied gives me the gives me that. That's what I'm that's what I'm kind of confused about right now. So I should do test circuit equals apply overlap test circuit. Okay? Yeah. Okay, now it works. Overlap is 1. Makes sense. Out at the end, so I'm calm. I like that. So it works for 1 qubit. So this is VQLS for 1 qubit with just the Hadamard overlay test as a and so, the idea is you want to minimize that, right? So, okay, the next video is I'm going to try to actually do that in Circ or maybe in Qisk. So I'm jumping into videos and I don't know. Good. So it kind of basically means, because they are not all 1. So I have A1. Okay, so why am I applying these twice? That's the point. What's the point here? So why am I applying? Gotta find a moment where I started building these earlier. I'm applying. I am doing the. I think I'm missing a video in here. I'm creating a circuit, am I not? Yeah, here it is. So what are you complaining about now? Is it that if I'm doing like 1,000 shots, those things kind of add up to 1,000, basically. So what I should do is, So what I should do is I should basically, that is really probably, I think I'm missing a video in here. Quantum intuition. So let me go, quantum intuition channel. I think I'm missing a video in between. Am I not? So the VQLS videos are here. Yeah. This is the video. I'll multiply them. No, that's not the video. That's not the video before that. These. Somehow the expectation value. I should just finish those things at once and not. Do I get to code at some point here? Quantum states is suggested you find the following. Maybe try to understand how this really works. That's not either. Like, where's the video? Part 3. That was part 3. I want part 2. VQLS. Part 2. The Hadamard test. Commentary. Oh, this is it, but I actually didn't have the. This is the video that I didn't have any audio. That's awesome. But maybe I can get the gist out of it. So. So this is B, yeah, but where is A1? Cost function. Da-na-na-na-na-na-na. So I don't know if I was not doing it wrong the whole, the whole time, where I didn't have to actually split that into. I'll leave it here because it's just too much of a. It's probably been too long of a video for just. But the point is, that would work. That could work if I don't have to split A, because then it's just one thing we're optimizing, right? So then it's just you've got like the harmonic. Yeah, exactly that would work. It just bothers me because I know I don't like doing this. I want to really finish this properly. And it bothers me why I did it this way. Maybe in the audio commentary it's 10 minutes. See the audio commentary here. It seems the health of turn this on. VQLS. I'll keep it short. Okay, I'll just keep this commentary. So how is my internet actually? Here it goes. So workspace. We're going to the workspace, and we're basically going to VQLS, and then Jupyter Notebook. Give me a second. Do I still have this folder? I'm going to pause for a second, okay? I just found the code. Oh, I just found the code. Oh, I just found the code. I'm so happy. I'm so happy. I learning. Why is it loading? Yeah. Okay. I'm trying to see if this is gonna. I'm so not used to using Visual Code Studio, but I kind of find it nice. Okay. So this is the code. What am I doing here? I make myself a bit smaller. Apply B. Okay. So let's just start from scratch. Okay. So let's apply this and then apply this and then. What am I doing here? So these are. Okay. So this is the. B is the solution. Yeah. Why do I get so why do I have so many qubits though? Why do I have so many qubits? It's still running. Apply A1. The overlap test. Post processing. Why do I have so many qubits? Because it was getting. Quantum circuit. It's got 6 qubits. Why do I have 6 qubits? Found the code, but I forgot what am I doing with it. Okay, so these run. But what is these fixed ansatz? Parameters? Oh yeah, that's just the ansatz. Okay, no, sorry. Do that again. But here, circx. Yeah, I forgot all the details of the way that I implemented these. So one is just a Z gate, then the overlap test. Then this is just a dummy stuff. Then there's this post processing where I was getting the circuit. I was creating 3 copies of the circuit because I wanted to measure the 3 different qubit pairs and do the actual test, the actual overlap test. And then the cost function was to get the fixed ansatz and then apply A1 only B get the overlaps and then do the same for the second circuit where it was just the identity. But why would I do it with the identity? So what bothers me is that I don't understand why I'm using. Just to give you an idea of what I did. So I actually kind of copied a bit of the base in here. the baseline. But I was, instead of using that cost function that they use in here, I'm trying to implement that with just the Heidelberg overlap test. Let me walk you quickly through. Okay, so I'm using the same example. Okay, I now get it. I'm using the same example, but trying to use just the overlap test. And so I got a split. Yeah, okay, I get it. So we've got the first, in the first cell is just the import stuff, and then I kind of created, I copied, that's basically copied from the paper, from the tutorial. So this is the fix ansatz, then apply B and apply A1. So the general strategy here is that, okay, I know, I just wasted your day probably watching this video. So I'm using the same example. And so the question is, can I not just use the Hadamard test? Well, I should keep track of what I'm doing, and I should just come back to all the projects earlier on. Now I get it. So I'm using the same example. I'm just using the same example, right? Which means I got to decompose into Z3 and the identity. And now what I want to try to understand, to show, is why these doesn't necessarily work. Because what I'm doing here is I'm combining the overlaps by multiplying them. But what I should do is, I was saying, half these. Half these. To say each contributes to the half. That's what I was saying now. And then what this is doing the, I don't know if this is going to work. Yeah. Oh, look at this. Actually, it's not doing bad. Not that bad. And then, so it's getting the arrays in here. And what I was doing, so and what that's the solution. So now it's getting, I don't know if this is going to work out though. I think I was just testing here. But what do I do now with these? So now with these, I get so it's getting out, right? Maybe I should now actually try to really stick to the way it was Jack who wrote this. So what happens if I do that? It's just the whole thing again. I don't know, what is it? What is these? What is the whole thing here printing at the end? So Jack's cost is 0.002. In my case, is 0.009. The array is different. And what is these? What is these? Classical cost function. So now I can cost function achieve very low, and when we calculate our classical cost function, we get, which agrees perfectly with what we measured. The vectors, these and these are very similar. Is this what Jack means? Being very similar? Because that's what he does here classically, right? So if I say print, this is what it's printing. Single check. What is doing? A1, A2, and A3. Okay. So it's actually calculating the with a coefficient set. B, and then we're doing I would need to actually copy the whole thing. Let me copy the whole thing. From the out point. So, and now let's see, print classical check. Let's see what happens. But I got something here. What's going on? Error. Apply fixed ansatz. It's missing the parameters. So I know, because it needs this. It needs the circuit. Yeah, because I changed that a little bit. That it actually needs the circuit, and it speeds the circuit. I changed it because I was not managing to get it to work exactly. Yeah. Sorry, scrolling too much. It shouldn't work though, right? According to my theory, if I could, have them to contribute half of the cost function, that's what I. Yeah. Yeah. I mean, it's not a good. That should be like close to 0.9, 0.9. This means the solution that it found, it's really not good. It's really not good. And even if we multiply this together, as I had it before. And this means it's just not good. Why is it not good? This is what I'm trying to figure out. Why is it not good? That's why you probably started watching this video, which started like about an hour ago, and I haven't really figured. God, yeah, it's even worse. So those things don't combine well, and I think the reason they don't combine well is because there's just no. It just doesn't make sense. It just doesn't make sense because um, the combination of two overlaps, like I'm calculating the overlap with a final vector b, um, and then trying to combine it with how another one combines, and it's a sum, and um, this sum just doesn't make sense because maybe one is overlapping really well and the other one as well, and so what? Like, it doesn't mean that the sum is going to overlap well, right? I think, yeah, because I mean, just check vector sum, right? I mean, like you're not like, if you find a vector, if I'm finding these that overlaps well and these that overlaps well, then I'm gonna, like, if once I'll add them, like the addition of those two vectors that I come up with, it's not gonna have good overlap. Well, it doesn't have to have a good overlap, right? Like if my solution vector is like these, and I found one that almost overlaps and another one that kind of maybe overlaps like that, so it's also good, right? Like, I'm still going to find, the sum of those vectors is still going to be this one, which is not like, it's got nothing to do with that. So that just doesn't work. And the reason is because I don't keep that equality. So my point here is that the I do not respect, like, it's not that it's not that I'm not respecting something, is that I'm not like, I can't do this. Like, I can't do what this cost function allows you to do, which is take the sums out, right? And then you can compute this portion for each, like this value for each of the plus components and add them up. I just can't do that. And because I can't do that, it means it's trash. And because it's trash, it means I'm done with VQLS. I'm done with VQLS. Yeah. Intuitively, I think that's the idea. I can't. That's why the overlap test doesn't work. It will work if it will be a product. It will work if it will be a product, I think. Whatever. And I'll put that code into GitHub, definitely. But it doesn't work. It doesn't work because of these. Yeah. I still feel though I'm not. Yeah. That's why you're coming up with something else in here, which is this cost function, which basically says it's a projection Hamiltonian. So how close to B it is, right? Like, you're projecting your state against B, and then you do I minus, because it's like, that's the identity. So you want 1 minus. You want you want to optimize that. So the 0 is you want to minimize the value. So the 0 is the right solution. That's why you do identity minus these. And so if you farther develop that, then you get with, you kind of get with those components, and then you just have to calculate those components. Yeah, and then those components can be calculated. they can be calculated this way, right? So this is something you can, develop like that, and then what you're basically saying is that's of course the addition of multiple coefficients, but you can take them, because at the end of the day, what we're doing is calculating expectation values. The expectation value of the whole thing is the sum of the expectation values of the parts. And so you can move those two things inside, and it's not that you're taking the sums out. It's that you can think of you're moving these inside, and you're moving kind of these inside as well. Yeah. Oh yeah, you're taking the sums out. That's also the way you put it. Way to put it. Yeah. Especially because it's all a product. That's why you can do it. But it's not the overlap, like the over. That's the point. The overlap of the overlap of A and these, right? Like the overlap of these with B is not the same as the sum of overlaps of each component and B. It's not that doesn't hold true, so I can't do that. And because I can't do that, that's rubbish. But if I didn't have to decompose the matrix, then it would work. The same I proved it work with one qubit. Yeah. So it doesn't work in this case because I'm decomposing it. Okay, cool. Yeah, so I probably said this 10 times already. Doesn't work. That's what I wanted to know. I think VQLS is done. Yeah. I wonder if there would be any other interesting cost function that you could think of using. But here they go with expectation values, because I guess expectation value works well because you can do these things. You can just sum expectation values but how do they develop that? Okay, so they do these and then they say expectation value of these. Okay, and that's how they break it up. Okay, yeah. That's a crucial part. Okay, so so you say this is what you want, right? Like that's the operator that projects you against B, and so what you want to do is the expectation value. That's your cost function is the expectation value of this operator. Why though? Why the expectation value? How do you know the expectation value is going to work? So the expectation value, so this is, okay, so why is expectation value so widely used, right? We use the projection Hamiltonian. But how do we know that minimizing this Hamiltonian? Okay, as a Hamiltonian, so what would do is it would collapse your vector, your state into, it would collapse. It would just project your state into B. And so if your state is really is almost B or like B, when you project it, what, it's going to have a high expectation value? That's what I've done fully. That's what I'm missing here. So if you, so if you, if you expectation value. If 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 it's B and you collapse it, the expectation value is gonna be what? Because the expectation value, right? Those are the different eigenvalues, right? What was the so expectation value? What is the expectation of experiment? Yeah, but the average of all possible outcomes of measurement. Consider your operator A, the expectation value is these limitation in quantum theory, the experimental status is kind of simple case arises when A is a projection. When A is a projection and thus has only the eigenvalues 0 and 1. He has no type of experiment. In this case, the value is why that's the kind of the question that I'm missing here is why does applying the expectation value here make sense? This is what I'm missing. The expectation value of these. So the expectation value of this operator applied to my state, right? Which is the potential solution. It will be it will be really small. It will be really small in case that state is almost the one that I'm looking for, and it will be really small because what? Because it doesn't affect it, or that's kind of what I'm missing. The logic is why does the expectation value work in here? It's yeah, maybe I should do a bit of more research in these. Why is expectation value the right? I'm missing a bit more of the actual intuition behind expectation values. I feel, but I get that it works, but I don't know why the choice of expectation value as being the thing that you minimize, being the actual cost function, is the expectation value of that Hamiltonian. I understand the Hamiltonian makes sense as a Hamiltonian that collapses this thing, but why is like, how do you know this? How do you know that the expectation value of that Hamiltonian is the correct one? Because the expectation value of the Hamiltonian will be, or what's more, the lowest level of the, or minimizing the expectation value is the one. So the solution is the one that minimizes expectation value. That's the link that I'm missing. Why that particular choice? Okay, but at least I prove that the overlap doesn't work because I can't just combine it. Because I need to decompose A. Perfect. Yeah, that was a long video for not a lot of insights, I guess. But that's learning.